So here we are. We are back on week 6, day 2, and we're going to be talking about, let's go to that slide there, and we're talking about the meeting and overtaking ship-to-ship interaction. And this is sometimes known, as I mentioned in one of the classes, sometimes the meeting situation is called the Texas chicken. So we're talking about the pressure waves, that's one way to think about it, between the ships that when they are interacting. We have something else called bank effect. That's known as cushion and suction, sometimes bank cushion and bank suction. Then what happens when you have that bank effect? Then the vessel is said to be taking a shear, kind of losing control, and the proper action that you would take if you were in that narrow channel situation. Now this is something which is all described, it's talked about in chapter 6 on notes on ship handling. So let's get to it. We'll go back to this diagram here because, or this image here. So here we are in a little bend in a channel, and the two ships coming at each other. They're approaching, and they're going to initiate this passing situation. Incredibly close, dangerously close, some would say, but they're using the pressure wave between the ship in order to make it all work out. So here we are, a gray ship and a blue ship. They are in a head-to-head situation. Now, if you're in deep water, there should be no reason why you would get this close. It's only, of course, when you're in a narrow channel component. And when that narrow channel component is added, that we are faced to having to put ourselves in this position. You know, there's just not room for us. Let me illustrate that differently. So here's two ships, you've got plenty of water all around, you're in the big ocean, and, they shouldn't be in this position. Obviously, they should be something like this, and they're going to pass by each other with a very, very safe margin. There would be no interaction between the ships. But when we add that, let's say that shoreline situation, and we'll have a country shoreline, a mountain on one side, and we'll have a city shoreline over here, but we now have a narrow channel. How wide is the channel? The channel is about a ship length, so let's say 600 or 700 feet long, or width. And we'll make it a little bit bigger. And the ships are having to come by. They're both trying to be in the middle of the channel until such a point, and then they're going to execute this maneuver, and they're going to go through. There's things happening all the way as I maneuver them along, and then there they go. Well, that's very simple to do, but let's reset those and let's walk through that. First, we'll do it on paper, and then we'll do it here on the table with the model ships, and I'll sort of walk it through in both ways. So let's go back to our first diagram, the one that we just looked at. So this is where we just came from, and then we'll go to the next diagram, and let's see what this does. The vessels are forced into the center of the channel. Now, why are vessels forced into the middle of the channel? Well, let's look at this. The safest place to be is in the middle of the road. If there was nothing else, if this gray ship wasn't here, the blue ship would be trying to find the sweet spot in between this side and this side of the channel. Captain, the pilot on this gray ship, is doing the same thing. And then they look up and they look through binoculars, they look at their radar, and they understand there's a vessel, a mile or half mile away. And they're going to get into this interactive. But they're going to hold on to this center of the channel more so than most people would think. When the vessels approach to approximately 1.5 ship lengths of each other, each ship initiates a turn. Now you'll notice that each ship, I've got that highlighted here, is turning to starboard. So there's some right rudder, and here's some right rudder. They both begin to turn, and they start that turn to starboard so that they, of course, can pass port to port. Now, when we get to this point, they moved ahead a few hundred feet. Now the bows are pretty much just a beam of each other. A left rudder is used. We shift the rudder. It was right rudder on each ship, and now they've shifted the rudder. Left rudder is used to begin moving each vessel's stern. Let's use the word kicking that stern to the starboard side. We want this stern to start to kick away in this direction, and we want this stern to kick away in a downward, or let's use the word southerly direction. And also notice that there's a positive pressure wave caused by the bow waves as they come together. There's positive pressure, and I'm just showing that as two positive plus signs, that there's a pressure wave between them. Now that helps to hold the vessels apart. So any motion of this, now both vessels having left rudder, it's going to translate mostly to the stern moving up here and the stern moving down here. The ships won't try to come together. They'll be held apart by this positive pressure wave. Now we progress just another 100 feet forward, give or take, and you'll notice that first of all, that positive pressure, now I'm switching that, we start to see a negative pressure over here. Now this is where both vessels want to collapse together. The blue ship wants to set down towards the south. The gray ship wants to move up towards the north. They want to stick together. A lot of people would say, and you're not wrong to say this, that there is a suction. They want to suck together. They want to suction together, that there is a low pressure created between the hulls. Now, you know, both ships are maybe traveling 4 or 5 knots at this time. So that's a closing speed. If you got 4 knots on one ship and 4 knots on the other ship, we've got an 8-knot closing speed. And using our rule of thumb, let's see, you're going 8 knots. That's 800 feet in 1 minute. So it only takes about a minute, less than a minute, for these two ships to pass by each other. Very, very quick. You know, it doesn't seem like, you know, it's not like an airliner that goes by each other, zoom, but it is, you know, in our terms, it's pretty darn quick. I'm going to go back and edit that. The Venturi effect is being felt between the two vessels, resulting in a lowering of pressure between the two hulls. Notice that we've shifted back, so now we're trying to combat that, and the blue ship is trying to fight that tendency to suck together, to come together with this vessel, and the gray ship is using back to right rudder. So you can imagine that a pilot or a captain is going from right rudder back to left rudder and back to right rudder, and it's fairly aggressive use of rudder all the time. Now, as both ships, you know, they're just about by each other. As a matter of fact, the bow of the gray ship has moved by the stern of the blue ship. At this point, the ships begin to feel a tendency to sort of swing into that hole in the water. Some people have said that. I don't think there's really a hole in the water where that ship is, behind the gray ship or behind the blue ship. But the ship wants to fall or put itself back into that space, back into the middle of the channel. There's a lot of things happening. As we talk about bank cushion and bank suction later on in the lecture, you'll see that. So there's a natural tendency for the ships to want to return to the channel. My last bullet here is caution is needed. Remember that all the while you're moving ahead. Use some modest rudder. The ships are going to want to find the center of the channel. They're almost going to want to do that by themselves. You don't have to be. You're being less aggressive with the rudder at this point. Now, as the bows clear, as they start to clear, both are coming clear. They're both going back to the center line of the channel, which I've now put back in place here. Let the bow of each ship fall gently off to port. Gray ship's going to port, blue ship's coming down to port. And I do ask the question here, by the way, what's happening with regards to bank effect at this point? So once we get to that point in the lecture, when we talk about bank effects, cushion and suction, think back to what I'm talking about right here. Let's try to remember to do that. Think back to this moment right here. And the forces, there's something else going on. Now, incidentally, this is probably the most dangerous, the most likely place. Statistically, there's been more ships that have come together right there, stern to stern, than have collided into their bows. Back at the beginning of this evolution, the pressure wave, the bow wave, pushes the ships apart. But what's happening here with the propeller wash, you get a good low pressure here. At the very last moment, when you think you're all in good shape, you get a drop in the pressure behind each vessel, and the sterns will come together. That's the most dangerous place. If I ask you a question on the test, what is the most dangerous phase or point in a meeting situation, narrow channel, ship interaction, say to me, it's at the end. It says the sterns just are almost clear. That's going to be the answer. As you go a little bit further, everything's good. You didn't hit. You're going by. You actually didn't have that collision. You're just both, almost ships are going to naturally want to just find themselves back in the middle of the channel. And like I said earlier, it all happens very quickly. This is about, these ships are alongside each other, you know, for maybe 30, 40, 50 seconds. Large ships going 4 or 5 knots. They're not there for a long time. It's real tenuous. You feel like you're too close. You wouldn't be there unless you were in a narrow channel in the first place. So that's a good way to go through it. There's a lot of textbooks, and you can follow this, but you'll always see the same sort of discussion. So I'm going to put this video underway. There's the pressure wave between the bows. Now you're just at that point where there's a little bit of suction. We're giving some back to some right rudder now, and then starting to straighten the rudders out, and the ships will bring it back, and they'll find the center of that channel. It's really something. And again, it's called the Texas chicken. Let's stop that, and we'll play that. We'll just play that one more time. And there it goes. There's that initial turn away from each other. There's the bow wave. Now, you don't really notice it, but there is that pressure buildup. I'm going to show you something interesting in a few videos here at the same place as this video was shot. So that's how it's done. So here the ships are coming away, and they're coming down in this narrow channel. And at about this point here, where they are ship length, the ship length and a half, each vessel is going to turn to starboard. They're going to come approaching each other. There's that positive pressure bow wave that builds up between the two of them. We continue on. We continue on. There's going to be a little bit of a shift of the rudder because this vessel wants to bring the stern down. This wants to parallel up to the bank, lift its stern up. As they get to this point, now we've got a negative pressure between the two ships. There's a negative pressure in here. So we have to, again, try to steer away from each other a little bit so that we don't suck together. There's going to be some low pressure in between. That's all because of the Venturi effect. Maybe you know about the Venturi effect. Maybe you know about the Bernoulli principle. You probably studied that in physics, or if here or back in high school. And there you would go. And there would be that tendency to happen, but you have to fight it a little bit. And provided they start to fall back, and provided you're not too close together, you're at that danger area there, you'll pass clear of each other. You don't want to be so close that the two deckhands who are back on the stern of that ship, that they can't, slap hands as they go by each other. We don't want to be doing that. They don't want to bump fists as they go by each other, because that's going to get to that collision right there. Smack, smack, smack. You want to be a little bit of separation. That's why we have pilots, right? You don't, a captain, a sea captain, isn't well-versed in this. It's a whole different skill set going across the ocean than piloting a ship, and we all know that. And there they go on their way. So there's the situation as I like to describe it. Now we're going to change things up. We're going to go ship-to-ship interaction when we are in an overtaking situation. In an overtaking situation. Let's see if we can set this up again with any kind of smooth activity here. And so we've got the ships. We've got the colorful ship with the containers on, and this vessel's doing 4 knots, and the ship behind it is now doing 6 knots. And they want to very, very slowly overtake each other. We're going to overtake them on the starboard side. So the container ship is going to move down. We're going to overtake them. The bulk carrier is going to go a little bit faster. Now there's similar forces that we're going to take, and we're going to have to look at here. But this is an overtaking situation. So we'll go back and we'll talk about how that happens. And so that's the ship-to-ship interaction when you're overtaking. Now, let's make some points about this. It's more dangerous than in a meeting situation. That might not be intuitive, but it is more dangerous. And I'll explain why. It's done at a reduced speed. Now, think about that for a minute. See, here's the key. It's done at a reduced relative speed. Remember when the two ships were coming together? Each ship was doing 4 and 5 knots. So you had a relative speed, or 8, 9, or maybe even 10 knots. So now we've got a ship in an overtaking situation. One ship is doing 4 knots. One ship is doing 6 knots. The relative speed, that's the reduced speed. The relative speed is only 2 knots. So those ships, they're exposed to the danger, to the risk, because they stay alongside each other, just as I've written in the third bullet, for a much longer period of time. They're subjected to the interactive forces for a longer period. And the last bullet says, nor is that interactive force helpful, in quotes here. You know, when the ships met in a meeting situation, the bow wave pushed the bows apart. It was helpful. We don't have that. This is mostly wanting to suck themselves together. There's not a whole lot of helpfulness here, if I can make up that term. As with any narrow channel exercise, it would be best to avoid it in the first place. Nobody would debate that if there wasn't another ship in the channel, you'd be better off if you could go through the channel just by yourself. If you don't need to overtake, if you don't need to put yourself at risk, certainly don't do that. But in any event, that's not always possible. For some reason, you just have to go by. You know, there's something happening in the port that you have to go by. You're going to be asked to pass that ship, Captain. The pilot's going to ask you to do that. That's the prescribed procedure. And so the watchword is extreme caution. We're going to walk this through. We got a ship, dark blue and the light blue. Dark blue ship is westbound, making 4 knots. It's in a narrow channel. The other ship is doing 6 knots. So we got 2 knots of relative speed. There's going to be overtaking communication on the radio. I'm going to overtake you. And in this case, the blue ship is going to decide to overtake him for whatever reason. It's going to decide to overtake the blue ship on the blue ship's port side. So the ship A and ship B drops down to the south side of the channel. And as we get to this point, what I want you to notice is ship A, right here, begins to feel the effect of ship B. There is enough water mass moving around this ship as it's being dragged along and pushed with this ship. I'm not saying that you would necessarily feel it in the balls of your feet standing up on the wheelhouse, but perhaps some type of a speed log would indicate that you would have a small amount of acceleration in a longitudinal direction. And as you got closer and closer here, as ship B came up, that bow wave from ship B would tend to push ship A, push the stern up to the north. If the stern goes to the north, this ship starts to take a little bit of a turn, kind of right down into the water where you think you want to be, where ship B wants to be. As we go a little bit further, at this stage, ship A will have a tendency to swing to starboard. As we start to approach, as the bow wave gets up here, now, unlike the previous slide where the bow of A wanted to come down this way, now the bow of A wants to be pushed off to starboard. That means that the stern is going to want to come together here. And there's some rotational motion around the slower and the faster ship. The slower ship wants to rotate. The stern wants to come down. So again, I want to just reiterate that this is not as good as the meeting situation. The forces don't act together, all combining to be successful for you. And there's a key thought here. As you think about these forces, remember which ship has more speed. You know, for a guy who spends a lot of time talking about go slow, think ahead, and be patient, this is probably one time where I'm going to say the ship behind going a little bit more speed, and we know this. If you have speed, you've got a little bit more control. Now, don't interpret what I'm saying. The ship B shouldn't be doing this at, at 15 knots. You're not a cowboy. Now let's get to this point here. This stage, the combined bow waves, the bow wave effect pushes both bows apart. You can imagine the bow wave combined here. You can almost visualize it. It wants to push both bows apart. Think about where the pivot points are. Both ships are moving ahead. And the suction, the Venturi effect happening back here, wants to suck the sterns together. So the pilots really have to be on their game at this point. This is the most dangerous phase. Kind of like the meeting situation, and when it's all over, this is the most dangerous phase of the evolution. Ship A is now being pulled along with Ship B because of the effect of Ship B's wake or its following wake. Ship A will actually have a little bit of acceleration. And the suction at the stern of B, we're going to have to talk about bank effectors too. That's why we have to do the next part of the lecture. That creates a strong couple, and that's what sort of brings them together. That's a possibility. So here we are. We're right back at it. Ship A is irresistibly drawn to the stern of B, the bow of A to the stern of B. Meanwhile, B only feels a minimal effect as it's maneuvering, but it sort of feels like Ship A that they're sort of squirrely and they're out of control, and the sterns and the bow come together here, and that's where the collisions, statistically, that's where the collisions happen. Now I want to show you a video. It's similar to this, and we'll go to this video here. Now what's going to happen? Ship with the red top is going to be overtaken by a container ship, a larger deadweight tonnage ship. This is a relatively small ship. You'll see that as they get side by side. We've really exaggerated this, and that this ship is going fast, real fast, and this ship is stopped. Almost you could compare this to this tanker is at the dock. It's not at the dock. You see it's just along the levee here. Now as it starts out, we'll play it probably 2 times, and so you can see what happens. Overtaking, it says a moored ship. Now notice that an outline has been put around this ship, and watch the red ship closely as you don't really see much movement in water, but watch what the red ship, how it responds. You see the stern moving away? It's going away from its outline, and then the red ship is being pulled back. It has a little bit of rotational. It gets pulled way off its original location, and then it starts to take off. Now watch this. The red ship, now you can see the size of the different ships. Now the red ship says, hey, I'm going with you. And watch how it actually pulls back. It's going to be sucked back to follow that container ship. That's a tremendous amount of force to have that happen. Those are the forces that happen when one ship overtakes another ship. May not be as dramatic as that because when the ships are both moving, they have a little bit more control. Let's watch that again. So here we come, overtaking a moored vessel. And you'll see that point just coming up right there. We start to notice it. There it goes. The stern of the red ship starts to move a little bit, moves off its drawing. Dramatic, dramatic, dramatic. That's why we keep our lines tight when we're at the dock, so that passing ships in the harbor and in the channel or in the river, as they go by, they're going out to sea, they're headed to port. And if you're tied up at the dock with slack lines, this is where ships who are tied up get into problems. The ship gets moving, the lines part, and then you've got some explaining to do at that point. Well, I think that's a pretty good illustration. Okay, so we've talked about the overtaking situation and all the forces that are going to come into play here. It's coming up, it's coming up, it's going to be this, and then it's going to be this, and then it's going to be a little bit squirrely. We're going to get by each other, and then that's where the things want to come together right there. Then there's the meeting situation we went through, and this at the end was the very dangerous situation. So we've been through that. Now we're going to talk about something else. We're just going to have one ship in the channel. We're not going to have anything else here. We're going to talk about bank effect. When I say bank, I'm talking about the side wall, the side of the channel. The side of the channel here and the north side of the channel over here. let's go back into the PowerPoint. This is known as bank effect, and we refer to it as cushion and suction. We'll explain what that means. So here's some things to consider. These are the forces resulting in the resulting action between your vessel and the banks and the bottom, to a degree, of a narrow channel. It's the forces and interaction between your vessel and another vessel passing close in a narrow channel. That's kind of what we alluded to in the first part of the lecture. So we got to think back. So if you're operating in a narrow channel, actually you're having the passing effect of the ships, either meeting or overtaking. You also have bank cushion, so we're going to have to deal with that as well. Bank cushion and bank suction occurs when a vessel nears the sidewall of a channel. It's what's called a hydrodynamic effect. It's a function of the shape of the channel, the size and shape of the hull of the ship, in other words, their deadweight tonnage and their block coefficient, and the size, or rather the speed of the vessel, how fast you're going. So let me ask you a question here. When a ship's moving through the water, is this what's happening? Do you have just a flat water undisturbed? And whether or not you see it or not, it's there. There is a bow wave, there's a stern wave, and there's a trough alongside. Now that's going to be more enhanced the faster you go. But even at a reduced speed, it's still there, it's still measurable. Your naked eye might not be able to perceive it, but it's there. There's a crest, it's called a riding wave, there's a crest, there's a trough, I've exaggerated it here, and there's a stern wave. This is a view of the ship in the narrow channel. This is the end-on view looking at the stern. We see there's stern waves back here. This is the bow-on view. You see that there's a big pile of water. And I can mention that there is a large pile of water here because the sidewalls of the bank constrict that bow waves from spreading out into, if it was open water, that bow wave could spread out and it wouldn't be anywhere near as high. It wouldn't appear to be as big. But because it's constrained by this sidewall here, it can't go off and it can't spread out. That's one of the big things. So a mariner has to think about the channel profile. You know, it may look when you're in the wheelhouse of the ship that it may look like a large expanse of open water. But this may only be 4 or 5 feet deep here. The channel might be well dredged and it might have this shape. And so we are going to experience channel effect, bank cushion and bank suction. On the other hand, it might look something like this. Maybe the channel wall actually extends out of the water, and maybe you're only going to have that effect really on one side or more so on this side than we would on this side, because this slope of this channel wall isn't as steep, and we're not going to experience the same effect. Look at another view here. It looks, you know, this is what it looks like on the surface, but we've got these buoys here. They're moored out there, buoys, and it might be deceiving. It might look like it's got a wide open expanse, but you may have some channel effect down here. Very interesting. Here's a picture of the state of Maine. Now look at the trees in the background. You first look at this. This is over in Germany in a place called the Keel Canal. You might think that we're tied up at the dock. No, we are underway. We are underway in the Keel Canal. I'm going to be very brief about this. The Keel Canal, so here's Denmark, here's Sweden, here's Germany, Hamburg. And so the Keel Canal goes right through here from the port, German port of Kiel, and it comes out in here into the North Sea, the English Channel area. And so the Keel Canal takes all day long. Here's some pictures of the training ship going through the Keel Canal. You can see how constrained it was. And we certainly experienced bank effect as we were going through there. And we'll just take a couple more views. Look at the density of traffic as we're going through this canal. And so we had a cookout that day on board the ship. And I think you can see that everybody's out there. It was a nice day. It was certainly fun going through farm country, but just look at the density of traffic here. So bank cushion and bank suction, the two effects occur at the same time. the results of these effects can be loss of directional control, losing control of the ability to steer your vessel, and the vessel may shear, in other words, skip across or take an aggressive loss of control across the channel and stick itself into the mud on the other side. That's kind of a big deal. Now, you remember I talked about this. Let's go back and think about that wave. And so we got to think about that wave and what's happening. I want to go back to my camera shot here. I'm going to go back to this one. And so this vessel is proceeding along this narrow channel. Now, as long as it's in the middle of the channel, the bow wave on this side, the port side, and the bow wave on the starboard side are equal. But if the ship gets over here, there is an imbalance of pressure forces around the ship. It has a bow wave on this side and this side, but those bow waves are going to be different. And I'll show you some data on that coming up. This is what happens. The ship's coming along, it's too close to the starboard side channel. You're actually having to hold some right rudder at this point. I'll put the pen down here as a big rudder. Has to indicate some. It's holding right rudder. It's sort of fighting itself to hold itself in there. And if you don't do that perfectly, what happens is the ship, it kind of wedges off the sidewall of the channel and it starts going over here, and you've got enough weight and momentum, and it's just plug that ship into the ground over here. And it does happen, and mariners know about it. In a way, we fear it. We watch out for it. It's called shearing across the channel. That's the shear right there. Well, why does it happen? How does it? It happens because we're not in the middle and all the forces are in balance. This is still dangerous, but you're in balance. When you're down here, it's out of balance. You know, what really happens here is you're going too fast. If you're going too fast, that's when you take a shear. You don't have enough time to stop. You're in trouble. You shear across the channel. Think about a 6, 7, 8, 900 foot container ship or a tanker going across and going into the shoreline over here. So obviously it is a problem. The net result of bank effect, the vessel will tend to shear away from the near bank. Now we're going to get in what's happening here. What's happening. So here's that ship, which is not on the center line of the channel, and there's positive, negative pressures alongside the vessel's hull. And I've indicated those by either a lot of positive pressure or a little bit, negative pressure or even more negative pressure. And here's the stern wave back here. But notice the imbalance because we're not in the middle of the channel. The bow wave on the starboard side is going to be because of this constrained area between the hull and this sidewall of the channel. That bow wave is actually going to appear to a casual observer who maybe was standing here looking at it. It would appear to be bigger. It's a bigger bow wave. There's going to be more cushion there. There's the bank cushion right there. It's bigger than the cushion, the bow wave on the port side, because there's more area for this to spread out. Now here's the trough alongside. I told you there's a riding wave, there's a crest, there's a trough, and then there's a stern wave, another crest on the stern. This gets into the Bernoulli principle. The trough alongside the near bank side is going to be deeper than the trough along the not near bank side. Now that's kind of a big thought right there. This trough is going to be deeper than this trough over here. Back here at the stern wave, because of the constriction, the stern wave might be a little bit greater. This one's probably going to be a little bit less. You know what happens here is that we end up with unequal forces around the pivot point. The ship's going ahead. There is a tendency, and I just used this to describe this, there's a tendency for us to shear off to port. There's a big cushion here, and here's the suction happening back here because of more low pressure on the bank side than on the other side. We got cushion here, and we got suction here. And the cushion outdoes the little cushion that's back at the stern. So we get some rotational aspect around the pivot point. That's what starts the shear. Boy, there's a lot to this. So we're going to do this diagram. I'm going to try to build this up here. Let's see, we've got a ship which is too near on the bank side of the channel. It's down on the south side of the channel. And I'm going to go over this in class, but we're going to use this diagram. We're just going to have to do this in class and talk about it on Monday. This is the water levels along the starboard side of the channel. And I'll talk about this in class. We're not going to go too far. And then here's the water levels on the port side. This is the starboard side of the ship. I think I may have said channel before. This is the water. There's the bow wave. Here's the trough. And there's the stern wave on the starboard side of the ship. And equal measurements were made for the port side. Remember, we were talking about this. It was this big bow wave, this trough, and this stern wave. And if I graph it out like this, it appears like that. These numbers refer to the height or the depth of the trough. This line represents the forward perpendicular, let's just say the bow, and this represents the after perpendicular, let's say the stern of the ship. And I'm going to flip back to that diagram again, and then we'll come down here. And then we're going to look at the port side. I'm going to flip up to this diagram. I'm going to talk about the port side here. Now, if you're lost, I don't blame you. It takes a while to get this. The bow wave, the trough, and the stern wave. See, the bow wave, the red bow wave isn't as big, it's not as high as the green bow wave. Here's the green bow wave, starboard. Here's the red bow wave, port. What gets interesting is when you lay them together. And here you see the imbalance graphed out. We see that the starboard side is a larger bow wave. You know what's particularly interesting, and I'll mention this in class, that's just about coincidentally where the pivot point is. If this is the line representing the bow, and this is the line representing the stern, and these are the troughs, right in this area, you can see how you should be able to understand why there's some rotational motion aspect to the ship. Well, as I said, in general, there are lower pressure areas on the starboard side, the channel bank side. The bow wave is higher, the depression is lower along the starboard side. The stern wave is larger, but it's not as large as the bow wave. It's all about not being balanced, and the result of that is that you take a shear. So let's talk about what do you do. This is almost the easy part. You know, when you lose control of something, just like in a car, you know, and you've probably felt this, you want to hit the brakes. But I think you've learned, anybody who drives in the Northeast or, you know, icy, snowy conditions, you've been taught that if you start to skid, you don't want to slam on the brakes because that's just going to make it worse. You don't, in I don't know, some sort of a comparative way. With a ship, stopping your engines if you are, or slowing down, that's not going to have any effect. So there are methods to control that shear. The best method is to maintain track as near to the center line of the channel. It's going to alleviate it, and just go slow. Maintain bare steerage way. Speed is what's going to really cause that shear to take place. But if it does happen, and if it does occur, what do? You control that shear with an aggressive use of rudder. So that's different than what they said when you're driving a car. But here's the deal. You touch the gas pedal on a ship, you increase your revolutions. You want to push more water by that rudder surface. And at all costs, if that doesn't work, you want to be dropping the anchor at short stay. And I'll talk about that in class. So those last few slides I know were really, really different. And so I'm going to stop there. We're done. We've played with we've done the model ships. Maybe that was helpful to have the model ships. We had the mountain shoreline, and we had the city shoreline. So I try to do everything, to just sort of illustrate this. been a long day. I'm sure it's been a long day for you and classes and meeting. Sometimes I just can't believe all the stuff that you guys, you students, that you have to do. I was looking over somebody's shoulder, had their computer open, and I was just looking at the sheer number of classes, Canvas classes that you have, you know, from each one of your classes, and then you've got, you know, you probably have a Canvas course, perhaps for athletics or different activities. And, you know, most of you've got stuff for, you got stuff for regimental, and you got ship stuff, and just overwhelming. I get that. And I don't want to make it any more load than just the bare minimum here. So stay with me. Hold on. November's coming. It's pretty good that we got this far. So take care. Adios. We'll see you on Monday, and talk to you later.